Good morning, everybody. My name's Matt. I'm here with my colleague Chris. We are data scientists at the NOC Enterprise Research Data Science Group at NOC. That's the nerds group at NOC. In this presentation, we're going to talk a little bit about who we are and what we do, and specifically about how we're using Apache Spark to address component degradation and unscheduled maintenance in the context of an aviation system. So here's our standard disclaimer. We don't speak for all of DoD or all of the Navy. Please feel free to read this on your own time. So who are we? We're a team of about 20 data scientists and engineers. We're based at NOC. That's a training command, the Naval Aviation Warfare Center Training Systems Division. They are in charge of procuring and maintaining naval aviation platforms, training for naval aviation platforms. So think these big, huge flight simulators. So those contracts all told total about $1 billion a year. So it's the largest modeling and simulation hub in the world. We're based in Orlando, Florida, so we're right next to the University of Central Florida. It's the largest undergraduate metropolitan research university in the world. So that's great for our talent pipeline. So we take the best and brightest out of UCF, and we turn them into civil servants and contractor support personnel in our group, all aligned kind of to the same goal. So Chris and I are both came out of that talent pipeline at UCF. Orlando, we're also right next to Disney World and Universal Studios. Some of you may have heard of that. And we're also just a quick drive from the Space Coast. So with the return to space at Cape Kennedy, with the Commercial Crew Transport Demo Mission 2, it's an exciting place to be. So what are we working on down in Orlando? Right now we're working on a tool called the Hornet Health Assessment and Readiness Tool. And it's not just us. This is a major collaboration, both in and out of the Navy, public, private, and academic. But HART is a real-time dashboard showing the maintenance status of an entire fleet of aircraft. So specifically, we're interested in understanding causes and being able to predict unscheduled maintenance actions. So an unscheduled maintenance action, as opposed to a scheduled maintenance action, is not something that is expected to occur. It's not related to a component service life or a scheduled inspection or anything like that. It's kind of like if you were to imagine that particular valve is not responding the way that it should somewhere in the aircraft, not responding to upstream inputs, and that's halfway through its expected service life. That would be an example of an unscheduled maintenance action. So the HART dashboard is responsible for showing the indicators that our team has come up with, and the other teams that we're working with have come up with, kind of showing how each aircraft in the fleet is doing along each of several metrics. So we try to roll that up into subsystems and into the ultimate airframe. And then we show that for the entire fleet. We'll get a little bit more into how we do that and how we do those roll-up scores and what's actually being calculated a little later in the presentation. So first, we're going to discuss what we're going to actually present, so how we're developing HART, the process that goes into developing HART. It all starts with our subject matter experts, or SMEs. These are the people that are the designers and the engineers and the maintainers on the aircraft responsible for making sure that it's capable of executing the mission. Next, we'll talk about how we set up our data pipelines to support our use cases, our ETL pipelines. Next, we'll talk about what kind of metrics we're looking at to try to determine the health of an aircraft and the health of a subsystem, and ultimately drill down into the component level. Then we'll discuss how we're deploying. So what kind of considerations should we take into account when we're considering where we're going to deploy and how we're going to deploy and how we're going to actually put all this into motion. And finally, we'll discuss how we incorporate user feedback into the development of the tool in terms both of the user interface and the user experience and the features that we're creating. So making sure that people are still getting value from this tool and that it's being able to be used effectively when making these kinds of maintenance decisions. So first of all, I want to kind of describe who our subject matter experts are and what role they play in the process. So subject matter experts, as I mentioned previously, are our engineers, designers, and maintainers. So here we've got 3 examples of how a subject matter expert might view the types of platforms that we work on. So aviation-related platforms here. On the left, we've got an SR-71 Blackbird, kind of with the propulsion and fuel subsystems highlighted here. The callouts relate to mostly components in those 2 subsystems. In the middle, we've got an example of the Space Transportation System. Some of you may know it better as the Space Shuttle. There's a couple of callouts related to maybe airframe proportions and aerodynamics. And on the far right, we have a satellite hub. And the callouts there are kind of higher level, right? So they're kind of like the thing that a systems engineer might consider, the large scale kind of work replaceable components. So this would be more towards like an operations and sustainment style engineer might. This might be how they think about the system. So this is just a few of the different types of subject matter experts that are responsible really for kind of becoming the data translators for us as the data scientists and the work that we do. Um, so to kind of get a little bit into how that happens, really the key ingredient is collaboration among the data scientists and the subject matter experts, as well as leadership and other components that you can see here. What it really takes to make this a success is for all sides to kind of have a generalist style approach to developing this kind of tool. Everyone kind of has to be willing to learn from one another, and specifically, you have to be willing to learn both from inside and outside of your team. So communication with both inside and outside of your team is really a key ingredient. So once you start to get engaged with those other external entities, you can kind of start to see how the pieces fit together and better understand which component and which subsystem you're trying to analyze. And ultimately, you start to educate both inside and outside of your team. You start trying to learn from people and sharing what you've learned. And all that contributes to this foundation of trust, this culture of trust. So it's really important that you have that key ingredient there. And why is that important? Well, say a subject matter expert were to come to me as a data scientist and ask me a question like, hey, whenever we have an aircraft that's, at maybe some number of thousands of feet and the pilot kind of slams the throttle forward and pulls back and then slams forward again and then there's a barrel roll and a loop-de-loop and does my subsystem perform the way it should? So maybe a fuel systems engineer might look at that and go, well, is the fuel system still able to adequately deliver proper fuel pressure and amounts throughout the aircraft? And so as a data scientist, I'm going to try to identify that condition in the fleet. I'm going to try to look through all my data and try to find where that happens. Then I'm going to compare the fuel system behavior to whatever is expected, except that I'm not an engineer. I'm not a subject matter expert. I don't necessarily know, to start off how that system is supposed to perform. So I'm going to reach back out to my network of subject matter experts and they're going to point me probably to some requirements documents or case studies or, just things that they, as the experts, have kind of incorporated. So without trust, they're not going to come to me, and I'm not going to get to learn that information, and they might not have their questions answered. So it's really a huge effort, truly, working with industry and other public partners throughout DoD and private partners as well and academic. It's really a big effort to try to come together and make this happen. So where the rubber really starts to meet the road here is when we say, okay, we're going to do predictive maintenance on an aircraft. Well, it's not quite that simple. You really have to break it down into its constituent parts first. You need to look at that and say, okay, I'm going to break it down into subsystems. So here we have a sample work breakdown for space shuttle, but you can kind of get the idea. You can see some of the subsystems there called out. So really breaking it down into a level that can be understood and addressed is kind of the key ingredient here. Especially since a lot of the aircraft that are flying today are what you might call legacy systems. So they weren't maybe necessarily designed with a data science first approach in mind. And they've also been around for quite a while. So some of the expertise has kind of moved on. And it's kind of a tricky thing to address because you've also got, some tribal knowledge in some groups. And our goal is really to pull all that together and make sure that, the knowledge that's captured anywhere can be applied everywhere so that we can, institutionally kind of apply the expertise to every single flight that we see. So while we're doing this, right, we're going to be kind of analyzing some data and we might see some data that doesn't quite look right. So first thing that I, as a data scientist, am going to do is I'm going to go out to my subject matter experts and say, hey, I'm looking at this subsystem and I'm looking at this data point. It doesn't quite look right. So they might come back to me and they say, oh, that's just kind of, a function of the way that particular component works. And if you analyze it like this, then it actually does make sense in the context of the rest of the flight. But if it does look weird to them, then it could just be that it's one of the idiosyncrasies of the data capture platform or just a function of the complexity of the aircraft. So I'm going to go ahead and hand it off to my colleague, Chris, and he'll walk you through some of our data science skills.
So thanks, Matt, for the handoff. And continuing to mirror what Matt has been saying so far, we're going to talk about some of the data complexity. For as complicated as the platform is mechanically, the data is equally complex. Mechanical systems rely on the interactions between various components, which introduce countless confounding effects into our data. This makes isolating and explaining behaviors of the data even more difficult. To further stack on top of that, because of software revisions and sensors added after development and different priorities and placed on different systems and aspects, recording rates can vary wildly. from purely discrete information to 1,000 hertz signals and everything in between. To further support this post-development insight that have been added as the rest of the system has advanced through the years, different software versions are deployed and can lead to varying types of data and columns, which may not be consistent or even may not be consistent between the same aircraft. So this brings us to our ETL pipeline. To handle all of this complexity and mixed data, we use some custom Python code in combination with the Apache Spark schemas to manage our ETL pipelines. We have two of them. They're quite similar, but serve different purposes and deal with two different types of input data. First is our batch analysis pipeline. This pipeline was built to handle already decoded flight data that's delivered to us daily and ingests to our on-premises compute cluster. Once we receive this data, it goes through our staging warehouse, where it's then cleaned and validated before being output to our analysis warehouse. The analysis warehouse is our working warehouse, where any of our feature development, data analysis, and model development is completed. Running in parallel, but on a remote system that we don't have access to, is our streaming pipeline. It takes in encoded flight data as it is uploaded from the aircraft, in which Kafka handles launching the decoding application and then sends it over to Spark Streaming to go through the same cleaning and validation that our batch analysis uses. Once Spark is finished with it, the cleaned and validated code is then sent over along with our features and models output to another analysis warehouse that's accessible from the dashboard. So this brings us to our data science cycle. While it's similar to most of the other data science life cycles that are out there, we found some things that we can focus on to make it easier for us. Dealing with this complex mixed data is difficult, and breaking the problem down to the slowest level has been really helpful in dividing the problem out and making it actually something we can tackle. The learning and understanding of a particular subsystem you're working on is absolutely critical to being able to make progress. Not developing this understanding means you're going to be asking more questions of the SME. It's going to take up both your times, and it's going to cause a delay in the progress to be made on the project. And then once you're finally up to speed with the domain for that subsystem, you can continue to work with the SME to define the problem you're trying to identify and create some potential indicators to find the component degradation that you're after. Once these initial indicators have been analyzed and you work through with the SMEs, features can begin to develop out of these indicators. And once the features are developed, you just work with the SME to refine them. False positive rates in our use case needs to be practically zero, as the only thing worse than unscheduled maintenance is useless maintenance. This cycle continues to iterate as both the SME and the data scientists continue to learn more about the subsystem data with every loop of this scenario. And this brings us to feature development. There are two main types of features we develop. There's logic-based features and deep learning-based features, or machine learning-based features, whichever you feel like calling it. Logic-based features are made by us essentially augmenting the SME's brains with our data science superpowers. Behaviors the SMEs have learned over the years, unofficial thresholds, and other tribal knowledge can be turned into code that operates on nothing but logic to detect degrading components. And while there exists error and fault detection on the aircraft, adding a new fault or an error on board may take a prohibitively long time. It could be, the better part of a decade or so, depending on how intense of an error it is to get it through the entire process. But what we can do is we can enhance existing error detection and enhance new errors by creating features that measure the exact same parameters and apply it historically all in a matter of days for a process that used to take years previously. Overall, the logic-based features we've developed so far have been moderately predictive in terms of finding component degradation. On the bottom left on the graph, using the NASA DashLink dataset, we have an example of a feature that we may create for something like this. In this case, we're looking at the rate of change of the fuel flowing from one tank to an engine. And let's say we have a theoretical threshold set at a rate of 200 pounds per hour is the fastest that feature should change. The potential feature in this case would count the number of times that we exceed that rate of change, and then that would be output to the dashboard as a feature to be viewed. Machine learning or deep learning features, on the other hand, were made to find things that the humans simply can't. We use a combination of Spark ML library and PyTorch for developing these features. Our main use cases for them is learning what normal behavior is and detecting complex parameter interactions. Predicting normal behavior is useful for when the behavior of one component depends on the other components around it, going back to that confounding effect I was speaking to earlier. And the logic itself is not enough to capture the complexity of this interaction. From the deep learning features we developed so far, we have found them to be highly predictive of component degradation, but they're not always the most trustworthy things because they sometimes have unexplainable behaviors and that's something we need to minimize by working with the SMEs. On the bottom right here, we have an example of a deep learning feature that may be made, again, using the NASA DashLink dataset. And in this case, it's one of our virtual sensor feature models. We'll discuss those on the next slide, but in the meantime, it attempts to predict the amount of fuel flow that is occurring in orange from this tank, given the rest of the aircraft's state and its recent states. It performs well overall, and it tracks the fuel flow, the actual fuel flow in blue overall. So this brings us to a little more discussion about the deep learning models that we use. We just wanted to take a minute and discuss them in a little further detail. The first type of deep learning model we use is anomaly detection. The goal here being to find unexplainable or errant behavior in an otherwise normally noisy data signal. Pictured on the top right there is the graph from the previous slide, which shows our virtual sensor model's fuel flow prediction against the actual fuel flow. In this case, you can see we highlighted two areas on that graph that appear to be potential anomalies. However, we found them not to be, as not only did the virtual sensor model pick up on the behavior and follow it, but we also looked into that flight in particular manually to determine that that was actually a normal behavior in response to something occurring in the aircraft. The second type of deep learning model we use are virtual sensors. These models excel in knowing what normal behavior is for a parameter, and they can pull double duty as anomaly detectors as well. They help with being able to model the behavior of a parameter that otherwise wouldn't exist, or to help fill in with data dropout that sometimes occurs. For targeting specific interactions between large amounts of parameters, we use information compression. We take the input data, pass it through an autoencoder that compresses it, and attempts to reconstruct it on the other side. By looking at the reconstruction error between the model input and output, as in the bottom right, we can use image classification then to determine what might be going wrong with the data. And this brings us to the deployment phase of everything. We've developed our features, we've established our features, refined them, worked with the SMEs to learn about them. And now we need to display them back to them in an explainable and an accurate way. And so before anything can be displayed, however, it needs to have some meaning of good and bad defined. These features output some score, but we don't actually know what they mean at the moment. So this is where feature score normalization comes in. We normalize the features using techniques like Johnson transforms and z-scores, and then we work with the SMEs to define a direction of bad for the feature's performance. This falls into one of your three general directions for a distribution. You have left-tailed, right-tailed, and two-tailed, and then we color code the feature score based on how far from the mean you get. We can see here that just 1 sigma away, you'll mostly be green. A little over 1 sigma away, you'll be going yellow. But then once you cross 2 sigma away, you'll end up being red. Displaying a few hundred features at all times is kind of unwieldy. You won't be able to realistically go through them all and pull any kind of meaning out of it quickly. So to do that, we need to aggregate the scores. On the bottom left here is a snippet from our dashboard that shows the aircraft's aggregate score. It kind of gives the SME an insight into the aircraft as a whole and the entire fleet all at once. So you're able to quickly target the aircraft that are showing as the least healthy aircraft. And then once the SME identifies an aircraft that they want to look further into, that whether it be something that's stationed where they're at or a particular aircraft that may have a problem that they saw earlier down the road, and then they can drill down further, like in the bottom right image there, where each column is a flight and each row is a feature for that subsystem, with that blue line representing a component replacement. So looking through time from left to right, we can see that this aircraft subsystem features started out doing okay. They were pretty green, and then we slowly gained more yellow, more orange, and then we started getting intermittent red before finally getting eventually complete consistent red, which indicates that that part has failed at this point. And then once we hit that blue line, we can see the component was replaced and everything went back to being okay. But having this dashboard is great. Hosting, securing, and updating the dashboard and the tool just doesn't happen automatically, which is why I'll turn it back over to Matt to discuss the deployment of HART.
Thank you, Chris. Yeah, that's right. So some of the things that we look at when we're deploying, we want to focus, our main focus is on speed, security, and live monitoring. You probably know these better by their other names: development, security, and operations. For speed, for us, it made sense so we've got our batch pipeline and our analysis pipeline. For us, just where we sit in the organization, it made sense for our batch processing pipeline, at least for our particular use case right now, to run on some on-prem hardware. So we went ahead and stood that up, and for the streaming stuff to be done in the cloud. So in both cases, we've tried to automate as much as we can. infrastructure as code, just trying to make sure that our builds are reproducible. For security, as a defense organization, it's our top priority. So we try to integrate ourselves into the risk management framework, the RMF, and make sure that we're operating under a CATO, or continuing authority to operate. One of the things that really helps a lot in this regard is an effort out of the Air Force Chief Software Officer Office. It's called the Platform One. Its goal is to harden COTS products, open source products, so they can be deployed to a secure registry, like a secure Docker registry. And so the idea there is you have your code, it gets built, it gets tested and scanned. And if your code passes their scans, then it gets pushed up to the secure registry. And, there's some paperwork on the back end to make it work, but that's the goal, right? So trying to get code that's built, tested automatically, scanned using these container and static analysis tools, and then ultimately pushed up to a secure registry where it can then be deployed on any certified cloud platform. So we primarily deploy to internal Navy clouds, and looking to expand that kind of. So ultimately, the last component there is live monitoring systems. This is our kind of operations dashboard, and it works well for ensuring that your technology is working well. But one of the things that you also need to be making sure is happening is that you are communicating with your users, and it's difficult to dashboard that user happiness, right? So you kind of need to reach out to your users at all stages, or we found that that's kind of the critical ingredient for us is constant communication with our users. So critical at all stages to the development cycle here. Everything, we have data questions about them. We have data science questions. We have questions about maybe how we should deploy and when we should deploy and where, what form the tool should ultimately take, what features should we include, what should we not. We bring in our users kind of at all stages, and for us, it really helps because our end users are the same people that assisted in the development of the tool, right? Our subject matter experts. So making sure that we're incorporating their needs into the tool itself, and that the tool continues to be useful to them, that it continues to be useful in a decision support role when we're making these kinds of decisions. Another thing that we found is to be really important is that these features are accurate and explainable. So if we want to, if we're gonna highlight an aircraft and say, this aircraft is going to need some unscheduled maintenance soon, we need to be able to defend that decision, whether we're using a logic-based feature or a machine learning or deep learning-based feature. It needs to be understood what exactly that feature is calculating, so that we can make sure that that our engineers and our end users ultimately understand what they're looking at with this tool. So communication is really critical at all points in this development process. So just wrapping up the development cycle real quick. This is our HART process laid out slightly differently. So, we've got this kind of continuous feedback loop going on. It starts with collaboration with the SMEs, and you and the SMEs, or we and the SMEs really are learning from one another, going back and forth. And then when we start to develop a product and we iterate, we say, okay, here's what it looks like now. What do you think? And they'll come back to us with some feedback, ultimately refining, mining out those false positives, making sure we're not generating any sort of nuisance alerts. Sharing our strategies on visualization, and coming up with a deployment strategy, and making sure that we're able to iterate quickly and fix problems when they start to come up, and just capturing feedback at all stages of the user cycle, making sure that we're incorporating what our users are telling us. So with that in mind, we've got now a process that we've been able to tailor to new subsystems and new components, and we're looking to expand it to new platforms as well, ultimately to meet the needs of the subject matter experts that reside in those particular domains. So what have we learned so far? One of the most important things that we've learned is that the data science role is kind of it helps really to have that domain expertise, and it's difficult to get that unless you're deeply embedded into the organization. And so having the ability to have subject matter experts right beside us when we're developing this kind of thing has really been invaluable. That's one of the key takeaways I think that we have found when coming up with this kind of predictive maintenance system for this complex mechanical system is the system experts absolutely have to be the central part of the conversation. Also, we found that without having the ability to learn from those experts, and from kind of teaching those experts what can be done with such vast quantities of data, you have to be willing to learn on both sides. We as data scientists had to learn a lot from our SMEs. We've got plenty more to learn. And at the same time, kind of teaching them like what kind of questions are they allowed to now ask now that they can leverage the entire set of fleet data. And finally, it's being such a large scale effort and working with such a complex system, especially a legacy system. It can't be done with just one team. Very difficult. So having the ability to lean on our data science partners inside and outside the organization, being able to leverage work that's been done throughout the organization is also very helpful. Where do we hope to take heart in the near future? Well, obviously, in collaboration with our partners, we're looking at starting to include additional subsystems and components and platforms. So think new aircraft. We're looking to include those and kind of roll up this cycle and this process that we've sort of hammered out over the last few years, kind of productifying it and applying it to new platforms. So the other thing we want to do really is be able to deploy this kind of thing at the edge. So, if an aircraft flies, there's no real reason if we're sure we can diagnose a particular degradation. There's no real reason for us to have to insert ourselves in the middle of the process there. We can say, well, okay, we know how to detect this. So, when you fly, you don't have to send us the data. You can run this kind of right there at the edge, right where the aircraft is. And then, if there is a particular feature that has a high confidence of correctly diagnosing a potential issue, then the action can be taken there. But we do have to be careful there. It's important that there's a sort of a formal process in place to be able to review that kind of feature because me as a data scientist, I might get it wrong. It's up. We have a great team behind us, and they're there to make sure that that nothing falls through the cracks on my end as well. So while we're kind of working towards applying this vast enterprise knowledge base to all the flights, there also needs to be some sanity checks in place to where the code that Chris and I write at the Nerds is also going to be sanity checked and validated by a review board of consisting of engineers and platform designers and what have you. So pushing that out to the edge and working out all the details on the way there is also something that we're very interested in doing. So we sort of discussed so far all the complex aviation use case, but we also feel that this process could be extended to other complex mechanical systems as well. So with that in mind, we'll go ahead and turn it over for questions.